A map of the infant universe should look random, like cold static left behind by the Big Bang. But hidden inside that ancient glow, scientists found something unsettling. Two of the largest patterns in the cosmic microwave background appear to point in the same direction, as if the universe has a secret axis. Even stranger, that direction seems to brush against the plane of our own solar system, a connection that should not exist at all. Is it a mistake in the data? A shadow from the Milky Way? Or the first hint that space itself has a hidden shape? If this kind of quiet cosmic mystery helps make the night feel deeper, leave a like, subscribe for more slow science stories, and share this video with someone who loves the unknown. Thank you for spending your time here. What time is it where you are watching? And where in the world are you? Leave a comment below. Now, let's step into the oldest light in the universe. The oldest light in the universe arrives from every direction at once. Faint, cold, and almost perfectly even, as though all of space still carries the softened glow of a fire that ended before any star existed. This light is called the cosmic microwave background, and it is not ordinary starlight. It is the cooled remnant of the early universe, released when space was still young, hot, and filled with a dense fog of particles, long before planets formed, long before galaxies settled into spirals and clusters, long before the sun gathered itself from a drifting cloud of gas. This radiation began its long journey across expanding space. By the time it reaches modern instruments, it is no longer visible to human eyes. It has stretched into microwaves, a whisper of heat only a few degrees above absolute cold. Yet inside that whisper is a map of the beginning. It carries tiny differences in temperature, slight, warm and cool patches that reveal how matter first began to gather, how gravity found its first uneven places, and how the later universe grew from delicate seeds almost too small to imagine. For cosmologists, the beauty of this map has always been its randomness. The warm and cool regions are not supposed to draw a great symbol across the sky. They are not supposed to prefer one direction over another. They are the faint imprint of quantum fluctuations, tiny early disturbances stretched to cosmic size. And in the standard picture of reality, those disturbances should be statistically equal wherever one looks. Space may contain galaxies, voids, clusters, and filaments. But on the largest scales, the universe is expected to forget all local structure and become smooth. There should be no cosmic north, no hidden up, no deep preference written into the whole. That expectation is quiet, but it is one of the pillars beneath modern cosmology. It allows scientists to treat the universe as broadly uniform, to build equations that describe expansion, gravity, and the growth of structure without having to ask whether space itself has a grain. But when researchers began to examine the largest patterns in the cosmic microwave background, a strange feature appeared. It was not a new galaxy, not a distant explosion, not a bright object sitting somewhere in the sky. It was an arrangement, a relationship between patterns that should have been unrelated. The broadest temperature features seemed to line up along a shared direction, as if the young universe had left behind something like a compass needle. At first, the signal was easy to doubt. The cosmic microwave background is faint, and the path between that ancient light and Earth is not empty. It must pass through the Milky Way, through dust, through charged particles, through the glow of nearer objects, and through the motion of the solar system itself. A false pattern can appear if a foreground is not removed perfectly, or if an instrument has a subtle bias, or if a statistical method turns random noise into something that feels meaningful. Scientists know this. The history of astronomy is filled with apparent wonders that later became artifacts of measurement. So the first response to the alignment was not wonder, but caution. The anomaly seemed too large in meaning to accept quickly. If it were real, it would point toward a universe more structured than the standard model allowed. If it were false, then it would be a lesson in how easily the human mind can see order in scattered data. The unsettling part was that the feature did not vanish at once. In the maps made by early precision satellites, the largest temperature patterns showed an odd coherence. Later, with better measurements and more refined instruments, the same basic unease remained. The alignment became known by a dramatic name: the axis of evil, not because it implied anything moral or supernatural, but because it threatened to damage a cherished assumption. In ordinary language, the name sounds theatrical. In scientific language, the concern is more restrained and more profound. The universe appeared to be offering a direction where no direction should exist. The temperature map did not merely contain small irregularities, which were expected. It contained a possible large-scale preference, a hint that the broadest features of the early cosmos were not arranged randomly. The problem begins with scale. Small temperature fluctuations in the cosmic microwave background are normal. They are the reason galaxies could eventually form. A perfectly smooth universe would have remained almost featureless, with no dense regions to grow into stars and no emptier regions to become voids. But the anomaly concerns the biggest patterns on the sky, patterns so broad that they span huge fractions of the observable universe. These are not ordinary local ripples. They belong to the largest modes that can be measured from Earth, the grandest variations in the ancient afterglow. According to the standard model, those broad modes should behave like independent notes in a quiet cosmic chord. One note may rise here, another may fall there, but their orientations should not conspire. They should not lean together. They should not form a shared axis. Yet, in the data, two of the most important large-scale modes appear to be unusually aligned. One divides the sky into broad opposing regions, and another divides it into a more complex set of warm and cool areas. In a simple, random universe, their preferred directions should be scattered. Instead, they seem to gather around nearly the same line. This is the heart of the impossible feeling. It is not impossible in the strict sense that nature forbids it. Randomness can always produce rare coincidences. A shuffled deck can arrange itself in a startling pattern. Dice can fall in an unlikely sequence. But science becomes uneasy when an unlikely pattern appears in the one place where a foundational theory says no pattern should be preferred. The alignment does not prove that cosmology is broken. It does not immediately overthrow the standard model, but it presses on a weak point. It asks whether the assumption of isotropy, the idea that the universe looks the same in every direction on large enough scales, is a practical truth or only a useful approximation. The answer matters because isotropy is not decorative. It is woven into the equations that describe cosmic history, the age of the universe, the rate of expansion, the role of dark matter, the influence of dark energy, and the interpretation of ancient light all depend on the belief that Earth does not occupy a directionally privileged viewpoint. This belief is part of the larger Copernican principle, the long scientific movement away from placing human observers at the center of things. Earth is not the center of the solar system. The Sun is not the center of the Milky Way. The Milky Way is not the center of the universe. More deeply, the place from which measurements are made is assumed to be ordinary. From one sufficiently large region to another, the same physical laws should apply, and the same broad structure should appear. The axis challenges this, not by claiming that Earth is special, but by presenting a pattern that appears strangely connected to the way the sky is seen from Earth. The most disturbing versions of the result suggest that the axis lies near the ecliptic, the plane of Earth's orbit around the Sun. This connection may still be a clue to a local contamination or a data processing artifact, and many scientists treat it with that suspicion. But if a relic from the early universe truly shares an orientation with the geometry of the solar system, then something has gone deeply wrong with the simplest reading of the cosmos. Either the ancient map has been stained by a nearby foreground, or the universe contains a structure that current theory has not learned to describe. In that uncertainty lies the power of the discovery. It is not a clean answer. It is a tension between the map and the model. On one side is an elegant picture of a universe that expands from a hot early state, smooth on the largest scales, seeded by random fluctuations, and shaped over billions of years by gravity. On the other side is a faint alignment in the oldest light, subtle enough to be argued over, persistent enough to resist dismissal, and large enough to make the whole picture feel less settled. This is how some of the most important scientific moments begin, not with certainty, but with a detail that refuses to fit. The axis may yet turn out to be a ghost produced by dust, motion, masking, statistics, or the difficulty of observing the whole sky from one small planetary system. It may be an elaborate coincidence, one that appears meaningful only because the human mind is sensitive to direction and pattern, but it may also be a sign that the universe is less symmetrical than assumed. It may point toward an early condition before the familiar laws took their present form, or toward a shape of space that wraps, stretches, or echoes in ways not yet fully seen. For now, the ancient light remains quiet. It does not explain itself. It simply carries its delicate warm and cool patches across cosmic time, and among them, perhaps, a line that should not be there. The first discovery is therefore not a single object hidden in darkness, but a question hidden in the background of everything. The universe, expected to have no preferred direction, may have left behind a direction after all. And that possibility is enough to turn a faint microwave glow into one of the most uncomfortable maps ever made. For a long time, the most powerful idea in cosmology was not a telescope, a satellite, or an equation, but a kind of humility. The universe, it said, should not be arranged around the observer. The ground beneath human feet may feel central because every horizon curves around it. But that feeling is a trick of perspective. Earth moves around the sun. The sun moves through the Milky Way. The Milky Way drifts among other galaxies. At every stage, a place that once seemed central becomes one location among many, embedded in a structure larger and older than itself. This gradual removal from the center is often gathered under the name of the Copernican principle. In its simplest form, it says that there is nothing specially privileged about the position from which the universe is observed. It does not mean that every place is identical in every detail. A star is different from a void. A galaxy cluster is different from intergalactic darkness. But on scales large enough for local accidents to blur together, the universe is expected to become statistically ordinary. No region should be the true center. No direction should be built into the whole. This assumption became one of the quiet foundations of modern cosmology because it allowed the universe to be studied as a coherent system rather than as an unknowable collection of special cases. If the same broad rules apply everywhere, then observations made from one galaxy can reveal the behavior of the whole cosmic expansion. If matter is distributed evenly enough at the largest scales, then the geometry of space can be described by a relatively simple cosmic model. If every direction is statistically equivalent, then the ancient radiation arriving from one side of the sky should carry the same kind of information as the radiation arriving from another. The power of this idea is difficult to overstate. It is the reason a map made near one small star can be used to infer the age, composition, and growth of the observable universe. It is the reason scientists can speak of a single cosmic history rather than a patchwork of unrelated histories. The Copernican principle is therefore not only a philosophical preference, it is a working rule that makes cosmology possible. From it comes the cosmological principle, the more formal statement that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means that, when averaged over enormous distances, matter is spread in much the same way, from place to place. Isotropic means that, from any given point, the universe looks much the same in every direction. These words are simple, but they carry a remarkable burden. They are built into the standard mathematical description of the expanding universe. They help define how space stretches, how light travels, and how the early fireball cools into the cosmic microwave background. Without them, the equations become much more difficult, and many familiar conclusions become less secure. A universe with a preferred direction is not just a universe with an odd feature on a map. It is a universe whose basic geometry may need to be rewritten. The standard model of cosmology, often called lambda CDM, depends on this smoothness as a deep background assumption. It combines ordinary matter, dark energy, and early cosmic expansion into a model that has been remarkably successful. It explains the abundance of light elements, the formation of large-scale structure, the pattern of acoustic ripples in the cosmic microwave background, and the broad history of expansion. It is not a fragile guess held together by one measurement. It is an elegant framework supported by many different observations. That is why the axis is so unsettling. It does not appear in a weak model already ready to collapse. It appears in a model that works so well that every anomaly becomes more significant. The better the theory, the sharper the discomfort when a piece of evidence refuses to settle into place. In a perfectly isotropic universe, the cosmic microwave background should have no meaningful orientation beyond the effects caused by local motion and foreground contamination. Once those are removed, the remaining fluctuations should be random in direction. Some patches are warmer, some are cooler, but the pattern should not arrange itself around a single grand line. There should be no axis that can be compared with the plane of the solar system. No deep alignment that seems to link the first light of the cosmos with the geometry of a much younger planetary system. The unremarkable universe should be indifferent to the path of Earth around the Sun. The ancient afterglow should not know, even indirectly, about the angle from which modern observers happen to view it. This is why the possible alignment feels almost like a philosophical wound. It seems to reopen a question that science had spent centuries closing. Modern cosmology replaced the older central picture with a colder and more freeing view. A vast universe in which no place is chosen, no direction carries special status, and life arises in one small corner without cosmic preference. The axis does not return the old picture. It does not prove that Earth is central, or that the universe is arranged for observation, or that ancient geocentric ideas were right. Such claims would go far beyond the data, but the anomaly does disturb the clean simplicity of the modern view. It suggests that the universe may contain a large-scale orientation that is visible from where Earth happens to be, even if the explanation is ultimately local, technical, or statistical. The coincidence touches the same sensitive nerve. It asks whether the assumption of ordinariness has been mistaken for a law of nature. Scientific humility can sometimes become an expectation. The Copernican principle began as a warning against self-importance, but in cosmology, it became something closer to a filter through which data is interpreted. When a measurement appears to imply a special viewpoint, the first instinct is to distrust the measurement. This instinct is healthy. Instruments have biases. Galaxies contaminate signals. Statistical samples mislead. Observers are surrounded by their own system of motion and dust and light. Yet the same instinct can also make it difficult to recognize a genuine feature if nature happens to be less symmetrical than expected. The universe is not required to respect the elegance of human assumptions. It does not have to be maximally simple. It does not have to remove every large-scale direction just because direction makes the mathematics less comfortable. The real issue is not whether a preferred axis feels philosophically unpleasant, but whether the evidence demands it. The history of the unremarkable universe is a history of successful simplification. By assuming large-scale sameness, scientists were able to reduce a nearly impossible problem to one that could be measured. The cosmic microwave background became a statistical field rather than a unique painted ceiling. Galaxy surveys became samples of a general structure rather than local curiosities. The expansion rate became a property of the universe rather than a direction-by-direction accident. These simplifications gave cosmology its precision. They allowed a discipline that once dealt in speculation to measure cosmic parameters with extraordinary care. But every simplification has a boundary. If the largest observed scales begin to show departures from isotropy, then the boundary may have been reached. The universe may be smooth only up to a point. Beyond that point, it may carry memories of conditions that the standard model averages away. A preferred direction could arise from several kinds of deeper structure. It might be the remnant of an early phase before inflation fully smoothed the cosmos. It might reflect a finite cosmic topology, where space wraps around itself and creates repeated paths for ancient light. It might come from a primordial field that once stretched across the young universe and guided the formation of patterns. It might even be an illusion produced by the difficulty of seeing the whole sky through the bright, moving, dusty neighborhood of the Milky Way. Each possibility preserves some part of the unremarkable universe while weakening another. A technical artifact protects the principle, but challenges confidence in the maps. A real cosmic topology protects the idea that Earth is not central, but admits that space has a global shape with preferred scales. A primordial field keeps the laws of physics universal, but allows the early universe to carry a directional imprint. A truly anisotropic geometry would be more radical, suggesting that direction is woven into spacetime itself. The reason the axis matters is that it forces these possibilities into view. It does not merely ask whether one line on one map is real. It asks how much of modern cosmology rests on the belief that the largest scales must be directionless. It asks whether ordinary location and uniform structure are discoveries or assumptions. For now, the answer remains unsettled. The unremarkable universe still stands because it explains so much with such economy. It remains the best working picture. The calm mathematical sea across which most observations still travel. But somewhere within that sea, the oldest light appears to lean. The lean may be a reflection from the observer's own shore, a faint mark left by local dust, motion, or chance. Or it may be a sign that the sea itself has a current. The Copernican principle taught science not to mistake perspective for truth. The axis now asks a quieter and more difficult question: whether the principle, once so liberating, has become a shadow of its own. The cosmic microwave background is not a picture in the ordinary sense. It is a surface made of time, a shell of ancient light surrounding every observer in every direction, carrying the last glow of a universe that was once too hot to be transparent. In its earliest state, The cosmos was not filled with stars shining through darkness. It was a dense, brilliant plasma, a restless mixture of light, électrons, and atomic nuclei, all packed so tightly that photons could not travel freely. Light existed, but it was trapped. Each photon moved only a short distance before striking another particle and scattering again, as though the whole universe were a luminous fog with no clear horizon. Space was expanding while this fog cooled. Gradually, the temperature fell enough for electrons to join with nuclei and form the first neutral atoms. When that happened, the fog thinned almost everywhere at once. Photons no longer collided constantly with free electrons. They slipped loose and began traveling through space. That release occurred when the universe was about 380,000 years old, and the light set free at that moment is still arriving. It has been stretched by expansion for almost the entire age of the cosmos, cooled from a hot visible glow into a faint microwave signal, and softened until it now rests only a little above absolute cold. Yet its weakness is deceptive. It is the oldest electromagnetic message that can be observed directly, and it preserves the conditions of the universe before galaxies, before planets, before chemistry had built the familiar richness of matter. To read it is to read a boundary beyond which ordinary light cannot go. The map of this radiation is almost perfectly smooth. That near smoothness is itself one of the great facts of cosmology. It shows that the early universe, across regions now separated by immense distances, had nearly the same temperature. The variation from one direction to another is tiny, so small that it must be measured with instruments designed to detect differences of only a few millionths of a degree. Those slight differences are the important part. They are the seeds of everything that later becomes structure. A slightly warmer or cooler patch marks a place where density, motion, or gravity differed by a minute amount from the cosmic average. Over time, gravity strengthened those differences. Denser regions pulled in more matter. Gas gathered, collapsed, heated, and eventually formed the first stars. Stars gathered into galaxies. Galaxies gathered into groups, clusters, filaments, and immense walls surrounding dark voids. In this way, the soft modeling of the cosmic microwave background becomes an early score for the later universe. It does not show galaxies directly, but it shows the first unevenness from which galaxies could grow. The challenge is that the background cannot be seen in isolation. The ancient signal is everywhere, but it is faint, and the sky between Earth and that signal is filled with nearer light. The Milky Way glows in microwaves and radio waves. Dust grains, warmed by starlight, emit their own radiation. Charged particles spiral through magnetic fields and produce broad foreground haze. Distant galaxies add unresolved points of emission. Even the motion of the solar system through space creates a strong temperature pattern, making one side of the sky appear slightly warmer and the opposite side slightly cooler. Before the cosmic microwave background can be studied in detail, these local and galactic effects must be modeled and subtracted. A clean map is therefore not raw nature. It is nature filtered through careful correction, calibration, and statistical reconstruction. This does not make the map unreliable by itself. All precision science depends on separating signal from noise. But it does mean that any surprising pattern in the background must be treated with patience. The same map that reveals the early universe can also carry shadows of the observer's own environment. The first all-sky measurements showed that the background had the expected basic form, a nearly perfect thermal glow spread across the heavens. Later missions measured the small fluctuations with far greater clarity. They transformed the background from a broad confirmation of the hot early universe into a detailed field of information. Each small variation could be compared with predictions from the standard model, the size of the ripples, their contrast, and their distribution helped reveal the amount of ordinary matter, the presence of dark matter, the geometry of space, and the influence of dark energy. In many ways, the cosmic microwave background became the strongest evidence that modern cosmology was on the right track. The match between theory and observation was not vague. It was sharply patterned, with peaks and troughs in the data that reflected waves moving through the early plasma before light escaped. These acoustic patterns were like frozen echoes of pressure and gravity. They showed a universe whose early behavior could be calculated with remarkable precision. Against that success, the large-scale anomaly became even more troubling. The largest patterns in the background are the hardest to interpret because there are so few of them. Small ripples can be measured in great numbers across the sky, allowing statistics to become powerful. Very broad features, however, span huge portions of the heavens. There are only a limited number of such patterns available to observe. This creates a special uncertainty known as cosmic variance, the unavoidable fact that observers have access to only one universe and one sky. A rare, large-scale feature may be a meaningful clue, or it may be a chance arrangement that cannot be averaged away because there is no second cosmos to compare with it. The axis lives in this difficult region. It does not appear as a bright object that can be revisited from another angle. It appears in the orientation of the broadest temperature modes, in the shape of the whole sky's ancient modeling. Its meaning depends on the deepest assumptions about randomness, observation, and what counts as evidence when the sample size is the universe itself. In the cleaned maps, the expected picture is one of directionless irregularity. Warm and cool patches should appear without forming a grand preferred line. The sky should have texture but not intent, variation but not alignment. Yet when the largest features are separated from the smaller ones, an unexpected coherence emerges. The broad pattern that divides the sky into large, warm, and cool regions appears to lean in a particular direction. Another large pattern, more complex but still vast, seems to lean with it. The two should have no reason to coordinate. They come from different mathematical components of the same ancient field, and in the standard view, they should point independently, shaped by random early fluctuations. Their apparent alignment gives the map its strange power. Nothing has been found sitting at the end of the axis. There is no beacon, no wall, no visible boundary. The anomaly is geometric. It is a relationship within the oldest light, a correlation in the arrangement of warmth and cold across the entire sky. This is why the cosmic microwave background is the proper stage for such a crisis. No younger observation carries the same authority. Galaxies have evolved for billions of years. Clusters have grown, merged, and disturbed one another. Local motion can complicate the interpretation of modern structure, but the background comes from a time before these later histories. It records the universe before the first stars turned on, when matter and radiation were still closely tied, and the future cosmic web existed only as faint contrast. If a directional pattern is truly present there, then the direction belongs not to late cosmic accident, but to the early conditions of reality. It would mean that the seed field itself was not fully isotropic, or that the space through which the light traveled imposed a directional imprint, or that some foreground has imitated the early universe with extraordinary precision. Each possibility is profound in a different way. A primordial direction points toward new physics. A propagation effect points toward unusual cosmic geometry. A foreground imitation points toward a hidden limitation in the way the cleanest maps have been made. For now, the ancient light offers both confidence and unease. It confirms the broad story of a hot, dense, beginning with extraordinary elegance. Yet within that confirmation lies a pattern that does not sit comfortably inside the simplest version of the story. The same radiation that supports the standard model also exposes one of its most persistent wounds. That is the quiet tension at the heart of the mystery. The cosmic microwave background is not a chaotic unknown. It is one of the most studied signals in science, measured by careful instruments, compared against refined theories, and used to build the current picture of cosmic history. Its authority is exactly why the anomaly matters. A strange pattern in a poorly understood map could be dismissed with little consequence. A strange pattern in the oldest and most successful map of the universe cannot be set aside so easily. The baby picture of the cosmos was expected to show random freckles of early structure. Instead, at the largest scales, it may show a faint tilt, a broad arrangement that behaves less like noise and more like memory. Whether that memory belongs to the universe itself or to the observing system remains unresolved. But the question begins here. In a field of microwaves colder than any natural place on Earth, where the first free light still surrounds the present like a quiet wall of time, the multipole puzzle begins with a simple difficulty. The cosmic microwave background covers the whole sky, but the whole sky is too large for the eye to read at once. Its warm and cool patches look like a mottled surface, beautiful but confusing, with no obvious line to follow. To understand it, cosmologists break the map into layers of scale. They separate the broadest features from the finer ripples, much as a complex sound can be separated into deep tones and higher notes. This method is called multipole expansion. It is not a physical cutting of the heavens, but a mathematical way of asking how much structure exists at each angular size. Smaller components describe the delicate speckling that carries much of the information about early sound waves in the hot plasma. Different scales tell different stories. The fine scales show the ordinary success of the standard model with remarkable precision. The largest scales contain only a few grand patterns, and among them are the quadrupole and the octupole, the two wide notes whose strange relationship became the core of the axis problem. The quadrupole is the simpler of the two. After the strong effect of local motion is removed, it is the broad pattern that divides the sky into large opposing regions of relative warmth and coolness. It does not describe individual hotspots or small ripples. It describes a vast imbalance, a shape so large that it belongs to the entire visible cosmic sphere. The octopole is more intricate, dividing the sky into a richer arrangement of broad patches, but it remains a large-scale feature, still far removed from the fine grain of the background. In the usual theory, these two components are separate expressions of the early universe's random seed field. They arise from the same overall process, but their orientations should not be locked together. The quadrupole should have its own accidental direction, and the octupole should have another. There is no ordinary mechanism in the standard model that requires them to share an axis. A random early universe may produce warm and cool regions, but it should not coordinate its broadest modes like instruments following the same hidden conductor. This is where the puzzle sharpens. When scientists calculated the preferred orientation of the quadrupole and compared it with the preferred orientation of the octupole, they found that the two appeared unusually aligned. The effect is not a bright streak drawn visibly across the raw map. It is subtler than that. It emerges only after the map is mathematically analyzed, after the great pattern of motion through the cosmic microwave background is subtracted, after galactic foregrounds are cleaned, and after the full sky is expressed in its large-scale components. Yet once it appears, it is difficult to ignore. The two broadest meaningful temperature patterns seem to lean toward the same direction. Their planes appear related. Their axes appear gathered. In a random field, this is allowed but unlikely. The oddness is not merely that something unlikely happened. Unlikely events happen constantly. The oddness is that the unlikely event happened in the largest available patterns, precisely where cosmology expects statistical indifference to be clearest. The word multipole can make the issue feel distant, as if the anomaly were only an abstract quirk of equations. In plainer terms, the early universe leaves a pattern across the sky. That pattern can be separated into broad shapes. The broad shapes should be independent. Instead, two of the grandest shapes seem to point together. A pair of dice can be rolled again. A deck can be shuffled again. The cosmic microwave background cannot be replaced by another universe for comparison. It offers a single realization of the early cosmos. And from that single realization, scientists must decide whether an alignment is a message, a mistake, or a rare accident. This is the burden of cosmic variance. On the largest scales, the sample is small by nature. There are many fine ripples in the map, but only a few whole sky modes. The uncertainty is not only a flaw in the instruments, it is built into the act of observing the universe from inside it. Still, the alignment gained attention because it did not sit alone as a vague impression. Researchers developed different methods for measuring preferred axes, comparing planes, and estimating how often such coherence should appear in random simulated skies. The exact level of statistical tension depends on the method, the map, the foreground cleaning, and the assumptions made during analysis. A slightly different mask over the Milky Way, a slightly different correction for local motion, or a slightly different definition of alignment can alter the strength of the anomaly. This is why careful cosmologists speak about the axis with restraint. It is not a simple discovery, like a new moon around a planet. It is a statistical pattern whose meaning depends on how the oldest light is processed and how randomness is defined. Yet the repeated appearance of the same broad relationship keeps the question alive. Instead, the puzzle remains in the uneasy middle, strong enough to disturb and weak enough to argue over. The quadrupole itself adds another layer of unease because it appears lower in strength than expected. In the standard model, large-scale fluctuations should have a typical amount of power, meaning a typical contrast between warm and cool regions. The observed quadrupole is unusually weak. A weak broad mode is not impossible, but when its orientation also seems linked to the octopole, the coincidence becomes harder to treat as ordinary. It is as though the largest note in the cosmic chord were not only quieter than expected, but also turned in an unexpected direction beside another note. The two facts may be unrelated. A low quadrupole could be a statistical accident, while the alignment could be another statistical accident, and the mind may be tempted to join them into a story, because stories feel more satisfying than separate quirks. But science cannot ignore the possibility that related anomalies may share a cause. If the largest scales were shaped by something missing from the standard model, then low power and alignment might be different faces of the same hidden structure. The reason no easy answer settles the matter is that the standard model works extremely well at smaller angular scales. The fine structure of the cosmic microwave background matches predictions with remarkable accuracy. The acoustic peaks, which reflect waves in the early plasma, form a pattern that has allowed scientists to estimate the contents and geometry of the universe with great confidence. Any explanation for the axis must therefore be delicate. It cannot destroy the successful parts of the map. It must affect the broadest modes while leaving the smaller ripples mostly intact. A crude error in the whole instrument would likely damage many scales, A simple failure of the standard model would likely appear across more of the data. The axis behaves more like a large-scale boundary condition, a whisper from the widest structure rather than a collapse of all cosmology. That is why theories of cosmic shape, early anisotropy, or primordial fields become tempting. They can influence the largest modes without rewriting every detail of the smaller ones. Yet, the more carefully the puzzle is described, the less it resembles a dramatic overthrow, and the more it resembles a quiet pressure. The quadrupole and octupole do not shout. They lean. They do not reveal a visible seam in space. They suggest a possible orientation in the deepest background field available. The scientific question is whether that lean is physical or procedural. A physical lean would mean that the early universe was not entirely directionless, or that space itself imposes a structure on the light traveling through it. A procedural lean would mean that the analysis has inherited direction from the observer's environment, from the Milky Way, the solar system, the satellite scanning pattern, or the necessary act of masking bright foregrounds. The difficulty is that both kinds of explanation can seem plausible. The local sky has many ways to contaminate ancient light. The early universe has many unknowns still hidden behind the surface of last scattering. The multipole puzzle remains powerful because it sits between these two forms of ignorance. It is born from the cleanest map available. Yet it may be shaped by the dirt in front of that map. It concerns the grandest patterns in nature. Yet it depends on fragile statistical judgments. It hints at a cosmic axis. In the end, the quadrupole and octupole are not merely technical names. They are the broadest, readable gestures in the oldest light. They are the scale on which the universe is expected to be most serene, most free of preference, most faithful to the idea that no direction is special. Their alignment is therefore a small mathematical fact with a large philosophical shadow. If it is a coincidence, it is a rare and inconvenient one. If it is an error, it is an error that has survived more scrutiny than many expected. If it is real, it may be the first sign that the universe carries a pattern too large to be seen by looking at galaxies alone. The map does not declare which answer is correct. It leaves only the image of two vast modes, formed before any star, appearing to turn together across the sky, as though the earliest light remembered a direction that the rest of cosmology had been built to forget. The deepest discomfort in the axis mystery comes not only from the possible alignment of the quadrupole and octupole, but from where that alignment seems to fall when it is projected onto the familiar sky. A preferred direction in the ancient universe would already be strange. A preferred direction that appears near the ecliptic feels stranger still. The ecliptic is the plane traced by Earth's orbit around the Sun, and by extension the apparent path the Sun follows across the sky over the course of a year. It is not a cosmic structure in the grand sense. It is a local geometry, born from the arrangement of one planetary system around one ordinary star. The cosmic microwave background, by contrast, belongs to a time before the Sun existed, before the Milky Way had its present form, before there were planets, rocks, oceans, or living observers to define seasons. These two scales should have nothing intimate to say to each other. One is the geometry of a small orbit inside a young stellar neighborhood. The other is the cooled radiation of the early universe, arriving from almost every direction after traveling across nearly all of observable time. When the broadest patterns in that ancient light appear to respect the same local plane, the mind naturally hesitates. Either the connection is a clue to contamination from the observing system, or it is a sign that the interpretation of the sky has brushed against something far deeper than expected. In sober cosmology, the first possibility is always taken seriously. The ecliptic is not merely an abstract line. It is woven into the practical act of measurement. Spacecraft that map the microwave sky often operate from positions and scanning strategies shaped by the Earth-Sun system, their thermal conditions, their viewing patterns, their calibrations, and their repeated sweeps across the heavens may all carry some relationship to the ecliptic. Dust and small bodies within the solar system also lie broadly near this plane. Even when their microwave emission is faint, precision maps must ask whether a trace of local material could leave a subtle pattern. Earth itself moves along the ecliptic, and the motion of the observer affects how the cosmic microwave background is seen. The largest obvious signal in the microwave sky is the dipole, the warm and cool split produced by the motion of the solar system relative to the background. Correcting that motion is necessary before the deeper fluctuations can be studied. If the correction is slightly imperfect, it could leak power into larger patterns and make the ancient background appear aligned with the geometry of the observer. In this view, the ecliptic connection does not make the anomaly more cosmic. It makes it more suspicious. A map of the beginning may be carrying a fingerprint from the instrument, the orbit, or the local environment. Yet suspicion does not erase the puzzle. If the alignment were a simple artifact, better instruments and improved analysis might be expected to weaken it decisively. Instead, the connection has remained awkward enough to keep returning in discussions of the anomaly. It does not become stronger in every analysis, and it does not satisfy every statistician, but it persists as a discomforting feature of the low multipoles. The ecliptic association is difficult because it points in two opposite interpretive directions at once. On one hand, it is exactly what a local systematic error might look like. On the other hand, if the cleaned maps are trustworthy, then the most local plane in observational astronomy appears to echo a pattern in the oldest light. Such a result would be almost absurdly coincidental. The solar system is young compared with the cosmic microwave background. Its plane was set by the rotation of a collapsing cloud of gas and dust long after the background radiation had been released. There is no ordinary causal path by which the early universe could know the later orientation of Earth's orbit, and no ordinary path by which Earth's orbit could reshape the first radiation across the entire sky. This is the logical wall that gives the axis its unsettling name. The problem is not that the ecliptic is special in a mystical way. The problem is that it is special only locally. In a truly isotropic universe, local coordinate systems should vanish from the cleaned cosmic signal. A planetary orbit should be useful for calendars, spacecraft navigation, and the apparent motion of the sun, not for organizing the broadest fluctuations in primordial radiation. If a feature in the cosmic microwave background lines up with the ecliptic, the natural assumption is that the feature may not be primordial at all. But if every known local explanation is insufficient, then the apparent local alignment becomes a far stranger kind of evidence. It suggests either a hidden systematic effect more subtle than expected, or a flaw in the assumption that the largest cosmic patterns and the observer's frame can be cleanly separated. The second option does not require Earth to be central. It may mean that the geometry through which light travels, the topology of space, or the way large-scale modes are observed from inside the universe can make certain alignments appear from particular locations without granting those locations any cosmic importance. A person inside a curved hall may see echoes arranged around their position, not because the hall was built for them, but because every point inside the hall creates its own pattern of return. The analogy is imperfect, but it shows how a local viewpoint and a global shape can become entangled. The ecliptic also matters because it turns an abstract statistical anomaly into something almost visible. The quadrupole and octupole are mathematical components, hard to imagine without specialized maps. The ecliptic, however, belongs to the everyday architecture of the sky. It is the path of the sun, the band along which the moon and planets wander, the plane that gives the solar system its flattened form. When the ancient microwave pattern is said to lean toward this plane, the mystery crosses from statistical language into spatial imagination. It becomes a question of orientation. Why should the earliest observable radiation seem arranged with respect to the same plane that organizes the nearest planets? The safest answer may still be that it should not, and therefore something in the measurement or processing remains misunderstood. But the persistence of the question reveals how precision cosmology often advances. An anomaly becomes important not because it is immediately believed, but because every attempt to dismiss it teaches more about the instrument, the foregrounds, and the assumptions built into the model. Even a false axis would be scientifically valuable if it exposed a subtle weakness in the way all sky microwave maps are made. A false pattern aligned with the ecliptic would reveal hidden couplings between scanning strategy, foreground cleaning, and large-scale reconstruction. It would improve future measurements by showing where the observer's footprint still remains. A real pattern, however, would be far more consequential. It would mean that the universe has preserved a directional signature so broad that it reaches into the first light, and so puzzling that it appears entangled with the frame from which that light is viewed. In that case, the ecliptic might not be the cause, but a marker, a coincidence that has drawn attention to a deeper orientation in the cosmos. Distinguishing these possibilities requires humility. The human eye is especially vulnerable to lines, planes, and apparent correspondences. When many directions can be tested, at least one may seem meaningful by chance. A feature aligned with the ecliptic attracts attention because the ecliptic is familiar. If it had aligned with another celestial reference, that too might have invited a story. This is the warning behind the look elsewhere effect. The tendency to find significance after searching broadly through possibilities. Cosmologists must therefore ask not only how unlikely the ecliptic alignment appears, but how many other alignments might have seemed equally remarkable if they had appeared instead. The statistical answer is not simple, because the anomaly was noticed within a web of related large-scale oddities rather than in a clean, pre-planned test. That ambiguity keeps the debate open. Still, the ecliptic connection remains one of the reasons the axis cannot be treated as a simple curiosity. It touches the core problem of observation from within the universe. There is no external platform from which the cosmic microwave background can be viewed. Every map is made from inside a galaxy, inside a solar system, by instruments moving along particular paths, looking through local dust, correcting for local velocity, and translating the whole sky into mathematical coordinates. The dream of cosmology is to subtract the local until only the universal remains. The axis asks whether that subtraction has been completed, or whether the universal itself is less independent of viewpoint than expected. The ancient light may be clean, or it may still carry a nearby shadow. It may reveal a cosmic direction, or it may reveal the last unremoved trace of the path taken by Earth around the Sun. The unsettling beauty of the ecliptic clue is that both readings begin from the same fact. A plane that should be irrelevant appears too close to the heart of the pattern. Until the remaining uncertainties are resolved, the axis hovers between embarrassment and revelation, between a local stain on the oldest map and a hint that the universe has allowed the smallest geometry nearby to point toward the largest geometry there is. Ghosts are not usually welcomed into science, but in precision cosmology, the word can be strangely useful. A ghost is not a thing in the universe itself. It is a pattern created by the act of looking, a shape that seems to belong to ancient reality but comes from dust, motion, Instruments, or mathematics. The axis anomaly has always been haunted by this possibility. Its meaning is so large that skepticism is not a barrier to understanding it, but an honest step. If the broadest structures in the cosmic microwave background truly align, then the universe may be less isotropic than the standard model assumes. But if the alignment is a ghost, then the lesson is different and still important. It would reveal how hard it is to extract a primordial signal from a sky crowded with nearby effects. The ancient light is faint, and the foreground is not faint at all. Before any claim about the shape of the universe can be trusted, every nearer source of imitation has to be examined. The strongest suspect is the Milky Way. From inside the galaxy, the view of the early universe is never clean. The disk of the Milky Way stretches across the sky as a bright band of stars, gas, magnetic fields, and dust. In microwave observations, it becomes a complicated foreground with several different kinds of emission. Dust grains warmed by starlight glow at long wavelengths. Fast electrons spiraling through galactic magnetic fields produce synchrotron radiation. Ionized gas adds another haze. These signals follow the structure of the galaxy, especially its disk, and they can be much stronger than the tiny temperature variations cosmologists are trying to measure in the background. To make a map of the cosmic microwave background, researchers must model these foregrounds and subtract them. The process is careful, but it is not magical. If the model removes too little or too much, a residual pattern can remain. A small leftover from the galaxy may spread across the cleaned map and masquerade as a large-scale cosmic feature. This is the core of foreground contamination. It does not require a dramatic failure. A subtle mismatch is enough. The largest multipoles are especially vulnerable because they describe broad structure across the whole sky. If a faint remnant of galactic emission has a large angular shape, it can influence exactly the modes where the axis appears. This is why the apparent relation to the ecliptic is often treated with suspicion. The Milky Way has its own plane. The solar system has another, and the procedures used to remove local signals can connect these coordinate systems in indirect ways. A foreground ghost does not have to be obvious. It can survive as a residual after the brightest part has been removed. Faint enough to avoid simple detection, but strong enough to nudge the quadrupole or octopole. Another suspect is the observer's motion. The solar system is moving relative to the cosmic microwave background, and that motion creates the largest temperature pattern in the microwave sky. In the direction of travel, photons are slightly blue-shifted and the sky appears warmer. In the opposite direction, photons are slightly red-shifted and the sky appears cooler. This motion-induced pattern is called the dipole, and it is far stronger than the primordial fluctuations of interest. Scientists remove it before analyzing the subtler structure. But the correction is not only a matter of subtracting one simple stripe. Motion also produces smaller secondary effects. It can mix power between different multipoles and create contributions that resemble part of the quadrupole. If the velocity correction, calibration, or beam response is imperfect, a little of this local motion can leak into the cleaned background. At the largest scales, that leak becomes serious because the signal being measured is so delicate. An artificial contribution could weaken the quadrupole, rotate its apparent plane, or increase its apparent connection with the octopole. This possibility is uncomfortable because the observer cannot step outside the motion to check the result. Every measurement is made by an instrument moving with the solar system, and every cosmic map has to undo that motion mathematically. The next suspect is the mask. The center of the Milky Way is so bright and complex that many analyses exclude it from the map. Cosmologists place a digital mask over the dirtiest parts of the sky and reconstruct or analyze the remaining regions. This is sensible, but it changes the problem. A full sphere has clean mathematical properties. A sphere with a large irregular band missing does not. When part of the sky is hidden, different multipoles can mix with one another. The reconstruction may borrow assumptions about what the missing region should contain. Even when those assumptions are reasonable, they can shape the lowest modes. A mask can act like a mold pressed onto the data, especially if the signal being studied is broad enough to care about the missing area. Critics of the axis have often pointed out that different masks, cleaning methods, and sky cuts can change the strength of the alignment. This does not prove the anomaly is false, but it shows that the largest patterns are not measured in the same direct way as smaller, cleaner features. They depend heavily on how the contaminated part of the sky is handled. There is also the instrument itself. A satellite does not simply stare at the universe with perfect eyes. It scans the sky according to a planned pattern. Its detectors have beams with shapes that may not be perfectly symmetric, and its electronics must be calibrated over time. Heat from the sun, Earth, or spacecraft components can create subtle variations. Detector noise can have slow drifts. A scanning pattern tied to the solar system may leave traces in the final map if not removed perfectly. Modern missions are designed with care to avoid these problems, and many potential biases are tested through simulations. Still, the axis lives where tiny imperfections matter. A feature spread over the whole sky can be created by effects too faint to look important in any single observation. Instrumental ghosts are frightening, not because they are likely to be large, but because the real signal is so small. The ancient background is measured through layers of correction, and each layer carries the possibility of leaving a direction behind. Beyond dust, motion, masks, and hardware lies a quieter suspect, statistics itself. A random sky will always contain some pattern that looks meaningful after the fact. This is the look elsewhere problem. If many possible anomalies are searched for, one of them may appear unlikely simply because so many chances existed for surprise. The axis was not predicted in advance by a widely accepted theory. It was noticed in the data, named after its disruptive effect, and then examined more closely. That does not make it invalid, but it does weaken simple probability claims. Once an oddity has been found, it is tempting to calculate how unlikely that exact oddity is. Yet the correct question is harder. How likely is it that any comparably striking large-scale pattern would appear somewhere in the map and attract attention? If the quadrupole and octupole had aligned with the galactic plane, or the dipole, or another celestial reference, scientists might also have been startled. Human minds are skilled at drawing significance around whatever pattern emerges. The danger is the natural difficulty of assigning probabilities after discovery. This is why skepticism about the axis is not merely conservative resistance. It is part of the discipline required when the universe provides only one observable sky. A laboratory experiment can be repeated. A particle collision can be counted many times. A cosmic microwave background map is a single realization of a cosmic process. Simulations can generate many artificial skies, but there is only one real one. The largest modes in that real sky may simply be unusual. They may sit in the tail of the expected distribution. Rare, but not revolutionary. In that case, the axis would be a statistical mirage, a pattern that feels profound because it lies close to human concepts of direction and place. Yet the ghost explanation has its own burden. It must explain why the alignment appears with enough persistence to survive different maps, different cleaning methods, and long scrutiny. A simple foreground error should change when frequencies change. A simple instrument error should weaken with a different mission. A simple statistical accident should feel less connected to other large-scale anomalies. The fact that these arguments continue means the ghost has not been caught. It remains possible, even plausible, but not proven. The axis therefore occupies a difficult scientific border. On one side, accepting it too quickly risks building new physics on an artifact. On the other, dismissing it too quickly risks hiding a real cosmic clue beneath a pile of technical explanations. Good science lives in that discomfort. It asks what survives when every known source of illusion is removed. For the axis, the answer is still not final. Galactic foregrounds may have left a trace. Motion corrections may have tilted the largest modes. Masks may have reshaped the statistics. Instruments may have added a faint preferred direction. Randomness may have played a rare trick. Any of these ghosts could explain a line that should not be there. But until one of them fully accounts for the anomaly, the cleaned maps continue to hold their uneasy shape. The oldest light may still be speaking from behind the foreground, or the foreground may still be whispering in the voice of the oldest light. The hope placed in the Planck satellite was, in many ways, a hope for silence. Not silence from the universe, but silence from the anomaly. The earlier maps from WMAP had already changed cosmology by measuring the cosmic microwave background with remarkable care. Yet they left behind the disturbing alignment of the largest temperature patterns. Many scientists expected that a more sensitive mission would dissolve the problem. The reasoning was calm and practical. If the axis had been caused by imperfect foreground removal, limited resolution, detector noise, or some subtle bias in the earlier instrument, then a newer satellite with broader frequency coverage and better precision should expose it. Planck was built to do exactly this kind of work. It observed the microwave sky across a wide range of frequencies, allowing researchers to distinguish the primordial background from nearer sources of emission with greater confidence. Dust, synchrotron radiation, and other galactic foregrounds behave differently at different wavelengths. By comparing the same sky through these different microwave windows, scientists could separate the ancient signal from the layers of local contamination more carefully than before. In this sense, Planck was not merely a sharper eye. It was a test of whether the axis belonged to the universe or to the machinery of observation. When the refined Planck maps arrived, the expected erasure did not happen. The large-scale anomalies remained recognizable. The low power in the broadest temperature pattern persisted. The unusual relationship between the quadrupole and octupole did not simply fade into statistical normality. The details shifted with analysis choices, as they always do in such delicate measurements. But the central discomfort survived. For those hoping that WMAP had seen a ghost, this was not the clean resolution they wanted. Planck had different detectors, different observing strategies, different frequency channels, and far greater sensitivity. A simple instrumental explanation became harder to maintain. If the same broad alignment appears in maps made by different missions, then the cause must either be a deeper, systematic effect shared by both analyses or something genuinely present in the microwave sky. Neither answer is easy. A shared systematic effect would have to be subtle enough to evade extensive testing, while consistent enough to imitate the same large-scale structure. A real sky feature would press directly against the assumption that the universe has no preferred direction. Planck, therefore, did not end the debate. It made the debate more serious. The mission strengthened the parts of cosmology that were already strong. Across the smaller angular scales, its measurements matched the standard model with extraordinary precision. The acoustic pattern of the early plasma, the amount of ordinary matter, the presence of dark matter, and the influence of dark energy all emerged with a coherence that confirmed the basic framework. This success matters because it prevents a simple story of failure. The cosmic microwave background did not become generally chaotic under Planck's gaze. It became more precise, more ordered, and more consistent with the standard model across most of its structure. The anomaly survived only in the broadest and most statistically delicate region, where the universe offers the fewest independent samples. This made it both less decisive and more intriguing. If all scales had failed, the standard model would be in obvious trouble. If no scales had failed, the axis would be forgotten. Instead, Planck revealed a universe whose detailed texture obeys the theory beautifully, while its largest gestures remain uneasy. That uneven pattern of success is one reason the axis continues to occupy a peculiar place in cosmology. The Planck results also forced scientists to think more carefully about what confirmation means. In ordinary language, to confirm something can sound final. In cosmology, especially at the largest scales, confirmation is often more modest. Planck confirmed that the anomaly was not an obvious one-mission error. It confirmed that the broad features noticed earlier were present in a more advanced analysis of the microwave sky. It did not confirm that the universe itself has a physical axis in the strongest possible sense. The distinction is crucial. A persistent feature in cleaned maps may still arise from foregrounds that are difficult for all missions to remove. Because every observer looks through the same galaxy, it may arise from the same local motion correction. Because every satellite travels with the solar system, it may arise from the same masked regions. Because the Milky Way blocks the same parts of the sky regardless of the instrument, Planck narrowed the field of possible ghosts. But it did not banish them all. The result was a more disciplined uncertainty. The axis could no longer be dismissed as merely the weakness of an earlier satellite, but it could not yet be crowned as new physics. This middle state is uncomfortable because science often feels clearest when a measurement either rises into discovery or falls into error. The axis did neither. It remained. Its persistence changed the tone of the question. Before Planck, the question could be phrased as whether the anomaly would survive better data. After Planck, the question became what kind of explanation could survive the anomaly. Foreground models were revisited. Statistical methods were sharpened. Different maps were compared. Researchers asked whether the quadrupole and octopole alignment depended too strongly on specific cleaning choices, whether the apparent ecliptic relation was truly significant, and whether the low power at large scales was connected to the same phenomenon. Some analyses treated the anomalies as separate weak oddities, none strong enough to demand new physics alone. Others considered whether their shared appearance suggested a common cause. Planck gave enough information for both temperaments to continue. The cautious could point to cosmic variance and residual foregrounds. The adventurous could point to persistence across missions and the strange coherence of the largest modes. The satellite became less like a judge and more like a witness whose testimony was clear in some details and ambiguous in its implications. There is a quiet lesson in that ambiguity. Instruments do not simply deliver truth. They deliver measurements. And measurements must be interpreted through models. Planck measured the microwave sky with exceptional precision. But the meaning of the largest scale patterns depends on assumptions about randomness, foregrounds, and cosmic geometry. The same map can be read as a statistical accident within a still successful model, or as the first hint that the model's deepest symmetry is incomplete. Neither reading is careless when stated properly. The difference lies in how much weight is placed on rare features. Conservative cosmology prefers not to multiply new laws when chance and known complications may suffice. Speculative cosmology asks whether repeated rare features are nature's way of showing where the old laws are too simple. Planck did not force a final choice between these instincts. It forced them to coexist under better evidence. That is why its refusal to silence the axis matters. It made the anomaly durable enough to deserve attention, but not clean enough to command agreement. In the calm language of data analysis, this is a low-significance tension, affected by a posteriori statistics and foreground uncertainty. In the larger story of cosmology, it is a crack that keeps its shape when the wall is inspected more closely. The universe presented a model of great power, and then, at the largest visible scales, it left a feature that does not rest comfortably inside that model. Planck sharpened both sides of the contradiction. It strengthened the standard picture while preserving the question that unsettles it. It showed that the cosmic microwave background is not a failed map, but a map with one region of deep strangeness. The broad patterns remain faint. The statistics remain debated, and the local sky remains suspicious. Yet the simple hope that better resolution would make the axis vanish has not been fulfilled. The oldest light, observed through a more refined instrument, still carries something like a lean. Whether that lean belongs to the early universe or to the last shadows of the observing frame remains unresolved. But after Planck, the anomaly could no longer be treated as a passing blemish on an immature map. It had become a surviving feature of the most precise portrait of the young cosmos, a quiet line still visible after the universe was asked, with better eyes, to explain itself. Temperature is only one way for ancient light to carry information. The cosmic microwave background also carries a quieter property, one that is harder to measure and potentially more revealing. This property is polarization, the orientation of the light's electric field as it travels through space. In ordinary terms, light can vibrate in different directions, and under certain conditions, those directions become organized. In the early universe, polarization was created when photons scattered off free electrons in the hot plasma just before the cosmic fog cleared. The pattern of that scattering depended on the local structure of the radiation field. Where light arrived at an electron with a slight imbalance from different directions, the scattered photon left with a preferred orientation. When neutral atoms formed and the photons escaped, that orientation traveled with them. The result is a second ancient map laid over the temperature map, weaker and more delicate, but born from the same surface of last scattering. For the axis mystery, polarization matters because it offers a second witness. A temperature anomaly alone can be blamed on many things. It may be shaped by foreground dust, by local motion, by map cleaning, by statistical chance, or by some subtle coupling in the instruments. But if the same preferred direction appears in polarization, the case becomes harder to dismiss. Temperature can be altered by many foreground processes. Polarization has its own foregrounds and its own difficulties, but it is not identical evidence. It is a related but independent trace of the early universe. If the quadrupole and octopole alignment is truly primordial, if it belongs to the geometry or initial conditions of the cosmos, then some echo of that large-scale order may also appear in the polarization field. If the alignment exists only in temperature, then the suspicion grows that it may be a surface effect, a coincidence, or a contamination specific to how the heat map was made. This is why polarization has been treated as a trial rather than a simple extension of the story. It asks the anomaly to prove that it has depth. The problem is that polarization is faint. The temperature variations in the cosmic microwave background are already tiny. But the polarization signal is weaker still. It must be extracted from a sky filled with polarized foregrounds from the Milky Way, especially dust grains aligned by galactic magnetic fields and charged particles spiraling through those fields. These local sources can create polarized microwave emission that is stronger than the primordial signal across large regions of the sky. Removing them requires measurements at multiple frequencies, careful modeling of galactic structure, and an acceptance that the cleaned result will carry larger uncertainty than the temperature map. The broadest polarization patterns are particularly difficult because they are sensitive to calibration, large-scale systematics, and incomplete sky coverage. A small error can look large when the signal being sought is spread across the entire sky. For this reason, polarization has not delivered the simple verdict that many hoped for. Instead of ending the debate, it has deepened the weighting. The polarization field is usually described in terms of two broad kinds of patterns. One is called an E-mode pattern, which has a gradient-like structure, somewhat like lines stretching and compressing without handedness. The other is called a B-mode pattern, which has a curling structure and is often discussed in connection with gravitational waves from the early universe or with distortions caused by intervening matter. The E-mode polarization is the more securely measured primordial component, and it is closely connected to the temperature fluctuations. In the Standard Model, temperature and E-mode polarization are correlated in particular ways because they come from the same early plasma. This relationship has been one of the successes of modern cosmology. It shows that the temperature map is not an isolated artifact, but part of a coherent physical picture. Yet the axis question asks something more specific. It asks whether the largest scale polarization patterns share the same strange orientation seen in the broad temperature modes. That is a much harder question than asking whether polarization generally agrees with the Standard Model. The large-scale signal is weak, and the relevant modes are few. There is not enough sky to average away every ambiguity. If a preferred direction appears, skeptics can ask whether it is a residual galactic effect. If it does not appear, others can ask whether the instruments were sensitive enough to see it. This creates a rare situation where both presence and absence can remain inconclusive. A faint match may be suggestive but contaminated. A faint mismatch may be meaningless if the noise is too high. The polarization trial, therefore, proceeds slowly, with each new analysis narrowing rather than closing the range of possibilities. Some studies have looked for large-scale alignments in polarization and found hints that are difficult to ignore, while other analyses emphasize that the uncertainties remain too large for a firm claim. This ambiguity is not a failure of effort. It reflects the difficulty of measuring a whisper beneath another whisper. The cosmic microwave background temperature map is already a delicate relic. Its polarization is more like the grain of the paper on which the relic was written. It can reveal whether the pattern belongs to the original document, but only if the grain can be separated from every stain left by time and foreground light. For a real cosmic axis, polarization would be important for another reason. It would connect the anomaly more directly to the moment when the radiation was released. Temperature patterns can be affected after emission by the motion of matter, by gravitational potentials along the path of light, and by foregrounds closer to Earth. Polarization is also affected by later processes, but its primordial large-scale structure is tightly tied to the scattering conditions at last contact between light and matter. If a matching axis were found there with strong significance, it would suggest that the directional pattern was present when the universe became transparent. That would place the origin of the anomaly very early, before stars, before galaxies, and long before the solar system's ecliptic plane existed. The explanation would then need to reach into early cosmic geometry, initial condition, or fields that shaped the plasma before the first atoms settled into neutrality. It would no longer be enough to speak of an accidental pattern in the temperature map alone. The universe would have written the same broad direction into two related but distinct properties of its first light. At the same time, the polarization test can never be interpreted without foreground humility. The Milky Way is not only bright, it is magnetized, structured, and polarized. Its dust grains are not randomly oriented. They tend to align with magnetic fields and emit polarized light that can stretch across large angular scales. This means that a false polarization axis is not hard to imagine. It could emerge from incomplete dust removal, from assumptions about the galactic magnetic field, or from the limited ability to model foregrounds where the galaxy is complex. Future measurements are therefore crucial, not because they promise drama, but because they promise cleaner separation, more sensitive instruments, better frequency coverage, and improved maps of galactic foregrounds can reduce the room in which the ghosts hide. The goal is not to force the anomaly into reality, but to learn whether it remains after the sky has been cleaned in a new way. There is a calm severity in this test. The axis cannot rely forever on the temperature map. If it is a real feature of the universe, it should leave fingerprints beyond one form of evidence. If it is only a statistical alignment among the largest heat patterns, then polarization may gradually loosen its grip on cosmology. The difficulty is that nature has placed the answer near the edge of what can be measured. The broadest polarization modes are precisely the ones most vulnerable to uncertainty, and they are also the ones that matter most. The result is a scientific pause, not empty, but charged with restraint. The data do not yet allow a simple sentence. They allow only a narrowing corridor. On one side is the possibility that polarization will confirm a preferred direction, pushing cosmology toward a universe with a deeper geometry or an early anisotropic imprint. On the other side is the possibility that improved polarization maps will fail to support the temperature anomaly, leaving the axis as an impressive but ultimately local or statistical illusion. Between those outcomes, the present remains unresolved. The second witness has entered the room, but its voice is faint. It speaks through polarized dust, instrument noise, cosmic variance, and the fragile memory of scattering in the early plasma. What it says may decide whether the axis is a mark on the universe or only a shadow on the map, until the signal becomes clearer. The oldest light continues to hold two layers of meaning: the warmth that first revealed the impossible line, and the orientation of the light itself, waiting to tell whether that line was truly written at the beginning. The axis would be easier to dismiss if it lived alone, sealed inside one temperature map of the oldest light. A single anomaly can be a statistical accident. A single map can carry a hidden stain. A single method can make one feature look more important than it is. For many years, this was the strongest comfort available to cautious cosmology. The quadrupole and octupole alignment was strange, but perhaps it belonged only to the delicate world of cosmic microwave background analysis, where foregrounds are difficult, the largest modes are few, and the observer has only one sky to examine. But a universe with a true preferred direction should not reveal itself in only one place. If space has a grain, if the early cosmos was shaped by a broad field, if the geometry of the whole is not completely isotropic, then other cosmic tracers may show related hints. Galaxies should not be arranged or moving in perfectly random ways on the largest scales. Distant quasars should not forget entirely the conditions that formed them. Clusters of galaxies should move according to the gravity around them. But if a deeper directional structure exists, their motion may carry a faint memory of it. This is why the search for other directional clues matters so much. The axis needs witnesses beyond the microwave background. It needs signs in the later universe, in matter rather than radiation, in structures that grew long after the first light was released. One of the most discussed hints is the phenomenon often called dark flow. The name sounds more mysterious than the measurement itself, which begins with a practical question. Galaxy clusters are enormous gatherings of galaxies, gas, and dark matter. They move through space under the influence of gravity, falling toward denser regions and away from emptier ones. Some motion is expected, but some studies have suggested that many distant clusters may share a coherent drift toward a broad region of the sky, a motion too large or too organized to be easily explained by the visible distribution of matter within the observable universe. The evidence is difficult because the effect is subtle. It is often searched for through the way hot gas in galaxy clusters slightly alters cosmic microwave background photons passing through it, a process connected to the motion of the cluster itself. The measurement is faint, tangled with noise, and sensitive to how clusters are selected and modeled. Some analyses have reported a large-scale flow. Others have found weaker evidence or no decisive confirmation. The cautious view is that dark flow remains uncertain. But as a narrative clue, it is important because it asks the same kind of question as the axis. Is matter, on the largest scales, moving with no preferred cosmic direction? Or is there a broad drift that current models do not fully explain? If a coherent flow were real, and if its direction overlapped meaningfully with the microwave axis, the implication would be striking. It could suggest that the anomaly is not only a pattern in ancient radiation, but a feature connected to the later movement of cosmic structure. A true dark flow might point toward mass or curvature beyond the observable horizon, toward an unevenness left from a larger universe, of which the visible part is only a region, or toward an early condition that gave matter a shared momentum. Such a flow would not automatically prove that the axis is physical. It might arise from measurement difficulty, selection effects, or incomplete knowledge of local, large-scale structure. But it would weaken the idea that all directional anomalies can be isolated and ignored. The same is true for quasar alignments. Another clue from a different part of the cosmic story. Quasars are brilliant centers of distant galaxies, powered by supermassive black holes surrounded by infalling material. Because they can shine across enormous distances, they act as markers of the young and distant universe. In the standard expectation, the orientations of quasars and their host systems should not be coordinated across vast separations unless some physical connection or shared formation history exists. Nearby structures can have related spins because they grow from the same cosmic web, but across distances of billions of light years. Any large-scale coherence becomes difficult to explain. Some surveys have suggested that certain quasar polarization directions or spin-related axes may not be completely random, but instead appear aligned over regions far larger than expected. These results are debated, and the interpretation is delicate. Polarization can be affected by dust, magnetic fields, selection effects, and the methods used to compare objects across the sky. Still, the possibility is unsettling. A black hole in one distant region should not seem to know the orientation of another black hole in a remote region unless both were shaped by something broader than their local environments. If such alignments are real, they may imply that the cosmic web itself has a memory of large-scale conditions, or that primordial fields influence the formation of structure across distances that challenge ordinary causal intuition. In a universe born from a nearly uniform early state, small quantum fluctuations are stretched and later amplified by gravity. This process can create the web of galaxies without requiring a universal compass. But if quasars, clusters, and the microwave background all hint at related directions, the picture changes from one anomaly to a pattern of anomalies. The strongest version of this case remains speculative. It depends on whether the reported alignments survive better data, whether their statistics are robust, and whether foreground effects can be ruled out. Yet the existence of these claims keeps the axis from being only a microwave puzzle. It invites a broader search for anisotropy in the visible universe. Galaxy surveys have also raised related questions in quieter forms. On large scales, the distribution of matter should approach uniformity. But the transition from clumpy structure to statistical smoothness is not always easy to define. The universe contains immense filaments, walls, and voids, some extending across breathtaking distances. These structures do not automatically violate the cosmological principle, because local clumpiness can coexist with large-scale average uniformity. But the more structure appears at extreme scales, the more carefully scientists must ask where the averaging truly begins. If surveys reveal hemispherical differences in galaxy counts, brightnesses, or motions, those differences may be caused by observation limits, dust in the Milky Way, calibration differences, or the way objects are selected. They may also be hints of a universe that has not fully smoothed out at the largest observable distances. The cosmic microwave background gives the early map. Galaxy surveys give the grown landscape. If the grown landscape shows subtle directional preferences, then the ancient map's strange lean becomes harder to dismiss as an isolated accident. There is a need for restraint here. Combining anomalies can be dangerous. Several weak hints do not always make one strong discovery. They can instead make a pattern built from uncertainties. A debated flow, a debated quasar alignment, and a debated microwave axis may share the same problem. Each sits near the edge of measurement. Each depends on complex corrections. And each can attract meaning because the human mind wants separate mysteries to belong to one larger story. In careful science, the direction, significance, and independence of each clue must be tested before they are woven together. If the same data choices, sky masks, or foregrounds influence multiple observations, then apparent agreement may not be independent. If many possible cosmic directions are examined after the fact, a few alignments may appear inevitable. Still, there is a reason these clues are watched. The standard model is strongest when different measurements point toward the same underlying story. The cosmic microwave background, galaxy clustering, gravitational lensing, and supernova distances all became powerful because they converged. If a new pattern of directional clues were to converge with similar discipline, it would deserve attention. A real preferred direction would probably not reveal itself through one perfect sign. It might first appear as a low-level alignment in ancient light, a puzzling motion in galaxy clusters, a statistical orientation among quasars, and a slight imbalance in the large-scale distribution of matter. At first, each piece would look uncertain. Only over time, with better instruments and more careful surveys, would the false pieces fall away and the real pattern, if there is one, remain. This is the quiet possibility behind the other directional clues. They do not yet form a settled map of an anisotropic universe. They form a set of questions that rhyme with the axis. Why should the oldest light lean? Why might some clusters appear to drift together? Why might distant quasar orientations seem less random than expected? Perhaps each question has a separate, ordinary answer. Perhaps the microwave axis is a statistical accident. Dark flow, a measurement difficulty. Quasar alignment, a selection effect. And galaxy scale imbalance, a foreground problem. That outcome would not be failure. It would make the standard model cleaner and the measurements better understood. But there is another possibility, softer and more radical, that the universe is revealing its structure through hints too broad to fit inside familiar categories. In that view, the axis is not alone. It is the first visible thread of a larger fabric. one that runs through radiation, matter, motion, and orientation. The cosmos may still be nearly uniform, but not perfectly directionless. It may have a faint grain, a remembered flow, a geometry whose influence appears only when the widest scales are allowed to speak together. The axis of evil becomes more unsettling when it is placed beside the other tensions gathering around modern cosmology. On its own, it can be treated as a strange feature of the largest microwave patterns, perhaps real, perhaps statistical, perhaps a difficult remnant of foreground cleaning. But it does not appear in a period of perfect calm. It appears at a time when the standard model of the universe, for all its power, is being pressed from several directions at once. That model, often called lambda CDM, has been extraordinarily successful because it turns the vast history of the cosmos into a small set of ingredients and rules. It describes a universe filled with ordinary matter, dark matter, and dark energy, expanding from a hot early state and growing structure through gravity. It assumes that, on the largest scales, the universe is homogeneous and isotropic, meaning broadly the same from place to place and direction to direction. Under those assumptions, the equations become elegant enough to predict the observed pattern of the cosmic microwave background, the formation of galaxies, and the broad expansion history of space. The model is not weak. It is one of the great achievements of modern science. Its problem is more subtle. It works so well across so much of the data that the remaining disagreements feel less like ordinary noise and more like messages from the edge of its domain. The most famous of these disagreements is the Hubble tension, the conflict over how fast the universe is expanding today. When scientists infer the expansion rate from the early universe, especially from the cosmic microwave background within the standard model, they obtain one value. When they measure the expansion more directly in the later universe, using distance ladders built from variable stars and supernovae, they tend to find a higher value. The difference is not enormous in everyday terms, but in precision cosmology, it is deeply important. The early universe and the late universe appear to be giving answers that do not comfortably overlap. At first, many expected the gap to shrink as measurements improved. That is often what happens. A calibration is refined. A foreground is understood. A distance scale is adjusted, and the tension softens. Instead, the disagreement has remained stubborn enough to become one of the central questions in the field. It may still arise from hidden systematic errors in one or more methods. Distance measurements are complicated, and early universe inference depends on the model being correct. But if the tension is real, then something in the standard picture is incomplete. Perhaps dark energy changes with time. Perhaps there is an unknown component in the early universe. Perhaps gravity behaves differently on the largest scales. Or perhaps the assumption of large-scale simplicity is not as safe as it once seemed. This is where the axis and the Hubble tension begin to speak to each other, not as proven parts of the same phenomenon, but as related pressures on the same foundation. The expansion rate, inferred from the cosmic microwave background, depends on a model that assumes isotropy. The meaning of the microwave map depends on the idea that the universe has no preferred direction. If the largest temperature patterns hint at anisotropy, then the early universe may not be as clean a reference frame as the model requires. A directional structure could, in principle, affect the way distances, expansion, and large-scale patterns are interpreted. It does not automatically solve the Hubble tension. The connection is not simple enough for one anomaly to explain another by itself. But both problems ask whether the universe can still be described as a smooth, directionless whole with one global expansion history. If the cosmos expands at the same rate in every direction and has the same average properties everywhere, then early and late measurements should eventually reconcile under the same framework. If the universe has a subtle large-scale gradient, a local underdensity, a preferred direction, or a more complex geometry, then the values measured from one region or one line of sight may not represent the whole in the way the model assumes. Some alternative ideas have explored whether the observer might live inside a vast cosmic void, a region with lower than average density. In such a setting, local expansion could differ from the cosmic average, because emptier regions expand differently from denser ones. This does not return Earth to a meaningful center in the old sense, but it does weaken the assumption that the local environment is perfectly representative. A void large enough to matter would be difficult to reconcile with many observations, and most versions face serious constraints. Yet the idea shows the kind of thinking forced by the current tensions. If measurements disagree, perhaps the issue is not only the measurements. Perhaps the map from local observation to universal conclusion is more complicated than expected. A similar thought applies to anisotropic expansion, where space might stretch slightly differently along different directions. Such models are highly constrained because the cosmic microwave background is so uniform, but the axis keeps them from disappearing entirely from imagination. Even a very small departure from perfect isotropy, if present at the largest scales, could influence how cosmic history is reconstructed. The standard model can absorb many small imperfections, but it is built on the promise that these imperfections average away. The axis asks whether some of them do not. The Hubble tension is not the only pressure point. Measurements of how matter clumps in the later universe have sometimes appeared slightly lower than what the cosmic microwave background predicts under the standard model. This is often discussed as a structure growth tension. It concerns whether galaxies and dark matter have gathered as strongly as expected over cosmic time. Again, the evidence is complex, and different surveys do not all speak with the same strength. But the pattern matters because it touches another prediction of lambda CDM. The early universe sets initial conditions. Gravity grows them. Dark energy slows that growth at late times. If the later universe appears a little smoother or less clumped than predicted, then perhaps the ingredients or rules are incomplete. A universe with subtle anisotropy or unusual large-scale geometry could affect the growth of structure in ways that are difficult to capture with a perfectly uniform model. It may not be the answer, but it belongs to the same widening field of questions. There are also large-scale features, such as unexpectedly large structures, hemispherical asymmetries, and possible differences in observations from one side of the sky to another. Many of these may fade with better data. Some may be consequences of selection effects or survey limitations, but together they create a sense that the largest scales remain less settled than the smaller ones. This is the opposite of what the simplest cosmological principle encourages. It suggests that averaging may work beautifully across many ranges, then become delicate near the horizon of what can be observed. Lambda CDM may be less a final cosmic architecture than a remarkably accurate approximation, one that captures the dominant behavior of the observable universe while smoothing away rare or very large features. That would not make the model a failure. Newtonian gravity did not become useless when relativity arrived. It became a limit, a powerful approximation within a wider theory. The same may eventually be true of the standard cosmological model. It may remain the best description for most measurements while being incomplete at the largest scales, earliest times, or deepest gravitational regimes. The axis of evil is dangerous to the model precisely because it targets a principle rather than a parameter. A wrong matter density can be adjusted. A wrong expansion rate can inspire a new ingredient. But a preferred cosmic direction questions the symmetry that allows the whole model to take its familiar form without isotropy. the equations become less simple. The universe may need to be described not by one average expansion, but by directional behavior. The cosmic microwave background may need to be interpreted not as a random field on a perfectly indifferent sky, but as a field shaped by global geometry or primordial order. This does not mean that every result in modern cosmology collapses. It means that the cleanest version of the story may be too smooth. The real universe may have a residual grain, a memory of initial conditions that inflation did not erase, or a topology that makes certain large modes behave differently. The crisis, if it is a crisis, is not a moment of ruin. It is a moment of refinement. Science often advances when a successful model is forced to become more honest about its boundaries. For now, Lambda CDM still stands because it explains far more than its rivals. Any replacement must preserve its triumphs while accounting for its tensions. And that is a difficult task. A new model cannot simply be more mysterious. It must predict the acoustic peaks, the abundance of elements, the distribution of galaxies, gravitational lensing, and the expansion history, while also explaining why the largest microwave modes seem strange and why different expansion measurements disagree. This is why cosmology has not rushed into a new paradigm. The old framework remains too useful to abandon, and the anomalies remain too unsettled to command revolution. Yet the pressure is real. The axis, the Hubble tension, and related discrepancies have changed the emotional landscape of the field. The universe no longer feels like a nearly completed puzzle with a few missing pieces. It feels more like a map whose central regions are beautifully drawn, while the edges reveal hints of another projection. The cracks in Lambda CDM are not empty gaps. They are places where the assumptions beneath the model become visible. The axis shows the assumption of directionlessness. The Hubble tension shows the assumption that early and late cosmic history fit inside one expansion narrative. Structure tensions show the assumption that matter growth follows the predicted path from the first fluctuations to the present web of galaxies. Any one of these may be resolved without upheaval. All of them together suggest that the universe may be asking for a wider language. The calmest conclusion is not that the standard model is wrong, but that it may not be the whole story. It may be the smooth surface of a deeper geometry, accurate enough to guide almost everything, yet unable to explain why the oldest light appears to lean, or why the expansion measured nearby does not quite match the expansion inferred from the beginning. In that unresolved space, the impossible discovery becomes part of a larger turning point. The cosmos still obeys patterns, but perhaps not the patterns that made it easiest to understand. The final possibility is that the axis is not an error in the map, but a clue about the shape of the room in which the map is being seen. Modern cosmology often begins with a universe that is flat or nearly flat on the largest scales, expanding smoothly, with no edge and no preferred direction. This is not because other shapes are impossible, but because the simplest shape has explained a great deal with very few assumptions, yet simplicity can hide alternatives. A universe can be finite without having a boundary. It can curve back on itself in ways that are difficult to picture because every familiar picture must be drawn from the outside. While the universe has no known outside from which it can be viewed, one common image is a torus, a shape that loops around itself. A two-dimensional creature living on the surface of such a world could travel straight ahead and eventually return to its starting point without ever meeting an edge. A higher dimensional version of this idea would be far stranger. But the principle is the same. Space might be connected to itself. Light traveling across enormous distances could take more than one path around the cosmic geometry. Patterns from the early universe could echo, overlap, or be suppressed depending on the size and shape of the hole. In such a cosmos, the largest microwave modes would not behave exactly as they do in an infinite, featureless space. They could carry the mark of the universe's global topology, the deep connectedness of space beyond the local curvature that ordinary measurements reveal. This kind of explanation is attractive because it does not require Earth to be central in a meaningful way. It allows the axis to arise from the architecture of the universe rather than from a privileged observer. If space wraps differently along different directions, then some large-scale fluctuations may fit poorly, while others fit well, just as certain notes resonate in a room and others fade. The quadrupole and octupole alignment could then be a resonance of cosmic shape, a sign that the widest possible patterns are constrained by the dimensions of the whole. The low strength of the broadest mode might also make sense if the universe does not have enough room, in one direction or another, to support fluctuations beyond a certain scale. This does not prove a wrapped cosmos. Searches for repeated circles or matching patterns in the microwave background have not delivered a simple confirmation. But topology remains a serious way to imagine how a universe can be nearly homogeneous and still not perfectly indifferent to direction. The axis might be a boundary condition, not a local mark, a whisper from the overall form of space. Another possibility reaches deeper into the mathematics of space-time itself. General relativity describes gravity through geometry, and in its usual form, the geometry is locally the same in all directions when no matter or fields single out a direction. But there are broader mathematical frameworks in which direction can matter more fundamentally. In an anisotropic spacetime, the fabric of the universe may have a grain, a subtle dependence on orientation built into its structure. This does not mean the speed of light would vary wildly, or that ordinary physics would fail in everyday life. Any such effect would have to be extremely small, because experiments and astronomical observations strongly limit departures from familiar symmetry. But, at the largest scales, over nearly the entire observable universe, even a tiny directional feature could leave a trace. It could influence the broadest microwave patterns, the growth of structure, or the way distant light accumulates distortions as it travels. In this view, the axis is not a stain on an otherwise directionless universe. It is a faint exposure of a deeper rule, one that standard cosmology has averaged away because the effect is almost invisible except at the widest scales. There are also explanations that reach back to the first instance of cosmic history. The early universe may have contained fields whose influence was later diluted but not completely erased. A primordial magnetic field, for example, would naturally have direction. Magnetic fields possess lines of orientation, and if such a field existed on vast scales before atoms formed, it could have shaped the plasma, affected the polarization of light, or influenced the later spin and motion of matter. The challenge is that any primordial field must be weak enough to avoid spoiling the many successful predictions of the standard model. It must leave only a delicate signature, not a loud disruption. Other early fields could play similar roles. Inflation, the rapid expansion thought to have smoothed the young universe, is usually imagined as erasing directional irregularities. But if inflation began from an anisotropic state, ended unevenly, or involved more than one field, it might have left residual structure on the largest observable scales. The smaller ripples would still look nearly standard, while the broadest modes might remember conditions from before the universe became smooth. The axis would then be a fossil not of a later object, but of an earlier phase, a time when symmetry had not yet fully settled. More speculative still is the idea that the universe's apparent three-dimensional reality may be related to information stored in a different way, on a more fundamental boundary or horizon. In such a holographic picture, the geometry of space is not the deepest layer. It emerges from information, and large-scale patterns may reflect the way that information is encoded. The axis, in this framework, could be an artifact of projection, not an error made by scientists, but a real feature of how a lower dimensional structure appears as a higher dimensional cosmos. This idea remains far from a complete explanation of the microwave anomaly. It belongs to the frontier, where gravity, quantum theory, and information meet, and its language is still more suggestive than settled. Yet it shows how far the axis can push thought. A line in the oldest light can become a question about whether space is fundamental, whether geometry is emergent, and whether cosmic direction is the shadow of a deeper informational order. Such ideas must be handled carefully. The mystery of the axis should not become an excuse to believe every elegant speculation. Nature is not obligated to choose the most dramatic explanation. The anomaly may still disappear under better foreground models. It may become less significant when polarization is measured more cleanly. It may remain an unusual but acceptable statistical feature of one observable sky. A rare alignment does not automatically open a doorway to new physics. The standard model continues to stand because it explains the overwhelming majority of cosmic evidence with remarkable precision. Any deeper theory must carry all of that success forward. It must explain why the acoustic patterns in the microwave background are so well described, why galaxies cluster as they do, why light elements have the abundances they have, and why cosmic expansion follows its observed history. A new geometry cannot merely be strange. It must be stricter than imagination, able to survive measurement after measurement. That is why the axis remains unresolved rather than revolutionary. It is too persistent to forget, but not decisive enough to rebuild the universe around it. This is the quiet power of the unknown. It does not tear the old structure down. It reveals where the old structure may be incomplete. The universe may be infinite and directionless after all, and the axis may be a chance arrangement sharpened by human attention. It may be a subtle foreground, the final local shadow on the cleanest ancient map, or it may be the first visible sign that the largest scales obey a geometry still beyond the standard equations, a geometry that curves, wraps, flows, or projects reality in ways not yet understood. Each possibility changes the meaning of the discovery. As error, it teaches humility about measurement. As coincidence, it teaches humility about randomness. As new physics, it teaches humility about the universe itself. The oldest light does not resolve the choice. It simply remains, surrounding every observer as a dim shell of memory, mostly smooth, delicately modeled, and perhaps faintly aligned. The question that began as a strange orientation in two broad patterns has widened into a question about the entire architecture of existence. Space may be simpler than the anomaly suggests. It may also be deeper than the model allows. Somewhere between those possibilities lies the reason the axis still matters. It is not proof that the universe has chosen a direction. It is proof that the universe has not yet finished resisting simple description. The ancient light remains where it has always been, surrounding the present with a silence older than stars. It does not answer in the language of certainty. It offers only its faint warmth, its delicate modeling, and the possibility of a line too large to see except through mathematics and patience. Around that line, explanations gather softly. Some are ordinary and cautious, made of dust, motion, masks, instruments, and chance. Others reach toward the deep architecture of space, toward hidden topology, early fields, and a universe whose shape may be more subtle than the smooth models first allowed. Between them, science continues without haste. It cleans the maps again. It measures polarization with greater care. It compares distant galaxies, flowing clusters, and the oldest radiation, not to force the cosmos into mystery, but to learn what remains after every easier answer has been tried. The axis may fade one day into the history of statistical mirages, remembered as a lesson in how difficult it is to observe the whole sky from one small moving world. Or it may grow clearer, becoming the first sign that the universe has a deeper orientation, a quiet grain running through the largest scales of reality. For now, it rests in uncertainty. And uncertainty is not emptiness. It is the space where better questions form. The universe is still vast, still mostly dark, still patient beyond human measure. Its first light continues to arrive, carrying a memory from the time before galaxies, before the sun, before the Earth had any orbit to trace. In that memory, there may be only randomness. There may be an error. There may be a hidden geometry. The mystery remains open, calm, and immense, written across the sky in a glow almost too cold to notice and too old to ignore.